Hi, everyone. We're going to get started now while people still filter in. I just want to introduce myself. I'm Marty Candice. I'm a computational and data science research specialist here in the High Performance Computing User Services Group here at SDSC. Today, we're holding this rescheduled training on the new RAPIDS framework from NVIDIA. I apologize about the rescheduling last week. The SSD on my hard drive died, and it created a lot of backup in my workflow for finishing both this talk and grant submission we were working on last week and a few other things. So I apologize for the delay in the training here, but hopefully you get something out of it today, and thanks for joining. So let's go ahead and get started. So again, just a quick thing about me. I'm working in the HPC User Services Group. I mostly work on Comet if it's one of the Exceed systems you're running on right now. My background is actually not in data science or machine learning. I'm more of a computational physicist by training in traditional HPC, sort of hybrid codes with MPI, OpenMP, sort of calculations for sort of computational fluid dynamic like simulation. So all of the material in here that I'll cover in Rapids is really data science oriented. So you might be more of an expert than I am on certain aspects of some of the libraries we'll talk about today, like Pandas or scikit-learn and things like that. So if you're here to really learn some intricacies of how Rapids translates over into a lot of the algorithms in those packages, I'm not the expert there, but we will have some other talks by NVIDIA next month that you can ask more in-depth questions to if you're interested. So just a disclaimer that I'm actually learning how to use all the data science tools such as Pandas, scikit-learn, and today Rapids myself. So hopefully this will at least give you an introduction to the material and get you going if you're sort of new to it all, like me as well. Okay. So just a few quick reminders before we get going. Just the Exceed Code of Conduct here. This is sort of a public forum. You know, you have the other participants. You can communicate with them through chat or communicate with us through chat. So if, just try to treat everybody with respect. And if you need to know more about the Exceed Code of Conduct, there's the link available here with contact information there as well. So, like I said, I work on Comet mostly. So just FYI, right, Comet's end of service is going to be March 2021 next year. So if you just applied for an Exceed allocation in January 15th, I think was the deadline, that'll be sort of the last full year of production if you get awarded. So just keep that in mind. And then we have the follow-on system, Expanse, which is the follow-on system to Comet coming in September 2020, roughly is when it'll be online. If you're interested in running on Expanse in the future, keep an eye out for any sort of announcements about maybe early user allocations and things might be before September 2020. But you'll again have to apply through the Exceed allocation process for those. So I don't think the details are set there, but just keep an eye out. Okay, so let's go ahead and get started. So the talk today, I call From Zero to Rapids, because that's sort of how I learned Rapids from the ground up, is just want to give you a quick high-level overview of what Rapids is, sort of what some of its capabilities are. And then I really just want to jump into a Jupyter Notebook demo and show you a little bit in-depth example about at least the first core library, which is called cuDF, which is sort of the Pandas drop-in replacement. I was hoping to get to the sort of scikit-learn drop-in replacement, which is called cuML, but I didn't have enough time to sort of sort through all the data and come up with a good example there. But I'll show you some links to additional resources and references for this Fannie Mae loan performance data set that we'll look at. It has some more in-depth sort of analysis. For example, there's one example that's going to use the Rapids framework also with PyTorch, if you're familiar with PyTorch too, to do some sort of machine learning on the data set as well. Okay, so that's sort of the overview of today, and let's just start talking about Rapids. So if you're not familiar with what Rapids is, it's NVIDIA's new suite of open source software libraries and APIs that sort of give you access to all of the sort of classical data science, analytics, machine learning type algorithms that you can run. You know, the idea is to run them much faster on NVIDIA GPUs than you can on traditional CPUs. So this is sort of the main goal. So what I'll show you, it's trying to really fill in, I think, a niche outside of sort of all of the sort of machine learning frameworks you kind of think of, like TensorFlow, PyTorch, MXNet, all these really frameworks that are targeted the, you know, very popular deep learning sort of applications these days, right? So Rapids is really trying to fill in sort of all of the more classical machine learning, data science algorithms that you're running in Pandas, scikit-learn, and some other libraries as well. So it's not really trying to compete with those deep learning libraries. It's really trying to fill in places where sort of GPU accelerated algorithms haven't been developed yet, or haven't been sort of put into a nice framework that you can use. So why might you want to use Rapids, right? So Rapids sort of leverages the underlying CUDA programming language and primitives to sort of get you those GPU compute optimizations without you having to do any sort of the programming, right? It's also, I think what you'll see is very user-friendly if you're familiar with sort of the sort of standard Python data science sort of ecosystem. So they're really aiming to develop very similar APIs to all of the you know, well-known data science and machine learning Pythonic sort of interfaces to a bunch of these libraries. And so the idea is to really get you working on GPUs as fast as possible. And so you'll kind of see that, I think, in the demo. Also, it allows you to, if you're familiar with Dask, which is sort of a framework to help parallelize a lot of these traditional Python-based data science and machine learning workflows across multiple CPUs. They also integrate Rapids with Dask to allow for sort of multi-node, multi-GPU systems if you have really large data sets, and it sort of allows you to scale out your analysis more quickly. I was hoping to get to an example of this in the notebook we'll go through, but I wasn't able to get everything set up quite. So it's sort of probably on the future roadmap of this talk of having sort of a full multi-node, multi-GPU example, because the data set we'll look at is actually large enough to really take advantage of and show you the advantages of this kind of setup. And then the last point is it's open source, so you can go see the source code and see what's going on and everything, what's going on. And sometimes you kind of have to do that right now. I mean, the documentation is still being formed. So if you can't figure out why sort of the Rapids version of this method is not working, you might have to sort of dig around in there and see how it's expecting sort of different input variables and things to be added in to your call to a certain method. So anyway, so that's sort of high-level overview of Rapids. So this is sort of the traditional CPU-based data science sort of software stack you might be familiar with if this is what you've been working with for a long time. So right, the two core libraries I would say Rapids is really trying to replace right now is Pandas and scikit-learn for GPU accelerate on their GPU. So they're really targeting all of the algorithms that you might be familiar with that are in those two libraries. That's sort of what's been most developed so far. If you're also using Network X for sort of graph analytics, there is a Rapids replacement for that right now. I think it's still one of the newer libraries that's being developed. So I haven't played with that at all, so I don't really have any experience with using that yet. So this is sort of your traditional CPU-based data science software stack that you're probably familiar with if you're here in this talk, right? So again, this is what Rapids is trying to do. It's really trying to replace. So your drop-in replacement for Pandas is going to be cuDF. This cuIO that's here on the screen, I'm not exactly sure what the difference is. They might be, I think, trying to split these libraries into two. when I was preparing this talk, it was the first time I'd seen the CUIO library show up, so I'm not exactly sure what sort of the future roadmap is here. Maybe they're splitting the existing version of cuDF into two. This is what it seems like from this chart. Again, cuML here is going to be your scikit-learn replacement, and cuGraph is sort of your network X replacement. So, and again, these are all integrated with Dask to help you do sort of multi-node, multi-GPU training if your data sets are that large. So I'm not going to go into any details, sort of the underlying architectures of the different libraries. I just want to give you a high-level overview if you're not familiar with these libraries, of what they are, and just some bullet points on that, and then we'll jump into the Jupyter Notebook demo and show you sort of how you can get started with cuDF. Okay, so I think I've kind of said this. So cuDF is your pandas replacement, right? It's sort of going to provide you with your sort of GPU native data frame library for essentially filtering and sorting and sort of exploring your data sets. And the idea is to really allow you to explore large data sets more quickly, essentially. Okay. So I said cuML, it's your scikit-learn GPU accelerated version. And it's going to have, again, they're trying to develop all of the same algorithms and methods that you might be using in scikit-learn in cuML. However, with all of these libraries, they're still undergoing lots of development. So certain algorithms may not be implemented yet. NVIDIA is pretty good, I think, about putting out a roadmap of what is on the roadmap and when you might expect certain algorithms to be available. Certain ones are important to your workflow, but just something to keep in mind that these libraries are changing quickly and new stuff is being added in, and so if something doesn't exist yet in Rapids, it probably will in the future if it exists in one of its sort of CPU brother libraries, essentially. Again, cuGraph is if you're familiar with Network X, which is for graph analytics. Some stats that sounded kind of interesting that I was reading about. So on a single NVIDIA GPU V100, you can get fit about 500 million edges of a graph, and you can scale to billions of edges if you go to multi-GPU. So it might give you, if you're, this is part of your workflow, some sort of graph analytics. Seems pretty interesting, how high you can go, how large of graphs you could really consider analyzing, where you might not even consider doing it on a CPU, because I don't think, as far as I understand, Network X isn't integrated with Dask, but that could be wrong. And the latest library that's been added into Rapids recently is cuSpatial. So this is a focused, specialized library on geospatial and spatiotemporal sort of data processing. So if you are doing sort of analyzing satellite data and have like geolocation data and things like that, this might be one of the Rapids libraries that you might want to look at and see what's being developed. I think it's very new. I think it's only in like the last few months that it came out. So I don't know exactly what's all in there yet, but if this is part of your workflow, some sort of geospatial data processing, this is one of the Rapids libraries you want to look at. Okay, so let's get to the more fun part. So I developed a Jupyter Notebook here based on one of the existing sort of demos that NVIDIA has out there, looking at this Fannie Mae mortgage loan data set. So if you don't know the reference here, The Big Short is a movie about the 2008 financial crisis, and particularly about the U.S. housing market. And so there's a book and a movie about it. It's actually both are pretty good. I've seen both. I've seen the movie and read the book. It's pretty good. And the data set that we'll look at covers sort of before the crisis and after the crisis. So it's kind of interesting for recent historical, economic and financial history, I guess. So it's sort of an interesting data set, and it's large enough to really show you how much faster rapids could be if you using rapids could be than sticking with your sort of same pandas sort of workflow or scikit-learn workflow. It's big enough to give you a sense of the speed up that you'll gain running on GPUs versus CPUs. Okay. So before I jump in the notebook, I just want to give you some context here about the data sets, what it means, what's some links to how to explore the data set further if you want to do it later on during your free time and get familiar with rapids. This is the data set. So it's the Fannie Mae single family loan performance data set. And there's a link here to the website where you can find it. And it's actually really nice in the sense that there's tutorials, there's R code and SAS code to analyze the data set if you're familiar with either of those languages for doing data analysis. So it's pretty well documented. It's constantly being updated. It's updated every quarter. And it's, I think I have some stats on the next slide. Yeah, so why are we gonna use this data set? So it's large in size, right? So it's more than 1.9 billion records on 37 million 30-year fixed rate mortgages. And uncompressed, the data set that we'll use today is around 200 gigabytes. However, we're going to use a subset of that because, as I said, I didn't do the multi-node and multi-GPU training. So 200 gigabytes isn't going to fit on a single GPU. So this is sort of why it's sort of an aspirational data set to keep developing this, this training to get to using the full data set and all the records in it. Like I said, its data set grows. So every quarter it's updated by Fannie Mae. You know, like I said, it's also well documented on the website on the previous slide. Fannie Mae, you'll see links to a couple tutorials on how to analyze the data set for, I think they're doing some sort of credit analysis on the, through those tutorials. And NVIDIA also has the data set featured in some of their previous Rapids training, so you can find material there. I think I put some links later on to one of the notebooks I mentioned where they use Rapids and PyTorch to analyze the data set. And it's easily accessible. So the data set you can get available for free from Fannie Mae on the website. You can just, you have to, I think, sign it, get a login to download it and any of the updates. But some of the subsets that are available on the NVIDIA Rapids website. So I'll just show you that here. So on the Rapids, in the Rapids documentation under the demonstrations, you'll find some subsets of the mortgage data set as well. Okay, so this is actually where we're going to download the data set you'll see in the notebook, but it's available here in the Rapids documentation as well. So you don't have to actually go sign up at the Fannie Mae website to get it. Okay, so just some additional context. So what is Fannie Mae? So if you're not familiar, this is the Federal National Mortgage Association. So Fannie Mae is sort of the its nickname. I don't know why, but that's the nickname. It's what's called a government-sponsored enterprise. So it's essentially a private company, but with certain sponsorship by the government, which essentially in this case really means that the U.S. government backs the debt of the company, essentially. So it's sort of one of these off-balance sheet items in the U.S. government national debt. It was founded in 1938, sort of at the sort of late stages of the Great Depression, to sort of get the mortgage market moving again in the U.S. So it created what's called a secondary mortgage market, which I'll talk about here briefly on the next slide. And some other history, became publicly traded in '68. And during the financial crisis, it was taken over by the federal government, and along with its sort of brother company, Freddie Mac. And in recent news, I guess they're actually talking about making them go private again. So it's kind of, like I said, an interesting data set with historical context and even for current events, I guess. So just to give you a sense of what the data set is and why it exists and what Fannie Mae does, what they do essentially is if you go get a mortgage at a bank for your house that you want to buy, you know, the bank will lend you or give you the mortgage, you get the house. when the bank takes on the mortgage, right, it's a debt that you have to pay back to the bank. What usually happens is, in most cases, or at least I think half of the cases of all U.S. housing loans, is the banks then sell the loan to Fannie Mae. Right? So Fannie Mae buys mortgages from banks to get them off the bank's balance sheets, essentially. What Fannie Mae does is then package those mortgages, which are talked about a lot in the Big Short movie I mentioned in the book. They package them into sort of larger bonds, essentially, that they sell as packages, a whole suite of mortgages contained in a single bond, and they sell those bonds, or what they call mortgage-backed securities, to investors, and they get the money back, right? So basically, Fannie Mae says, okay, we'll sell you this mortgage-backed security, and by the way, it's guaranteed by the federal government, so it's pretty safe bet that you're going to get your money back. That's why the investors buy these mortgages. So that's sort of the overview of how Fannie Mae fits into sort of the financial system, and why this data set exists, and sort of, because of the housing crisis, this data set is now public because they want to try to provide more transparency of how many loans are being made, what sort of debt is being backed, and things like that. Okay. So how big is, how much money do Freddie and Fannie Mae actually hold? So this is, I think, a chart I found from a 2016 article, and so then it was about $5.7 trillion is guaranteed through Freddie and Fannie. I'm not sure how it breaks down percentage-wise, but this is sort of the best sort of size of what this data set sort of is a subset of, representing how much debt and mortgages are backed by these two companies. And I think the recent article I saw in 2019 was it's up to 7 trillion. So this keeps going up and up and up. And so lots of the mortgages, so your mortgage, if it fits in certain terms, might be owned by Freddie or Fannie. And so, yeah, this is the last slide, just sort of to give the context. So all of the mortgages that we'll see in the data set are what are called conforming mortgage loans. And so essentially it's the primary type of loans that the Fannie Mae and these other government-sponsored entities can purchase. So this is, to give you context, like the main limit that creates a conforming loan is really how much the loan can be, what's the maximum amount a loan can be, right? So that'll show up in the data set of like how many loans are at a certain price, essentially, right? So this is some important context to have. And so in 2019, and it changes over time. So you'll have to look, if you really want to do some in-depth analysis, you have to look up sort of what the conforming loan limit was in a certain year, like in 2019. So any mortgage under $484,350 was a conforming loan, and so Fannie Mae probably bought that kind of loan, right? Obviously, so I live in California. Some of you probably live in higher cost areas. There are some higher limit loans you'll see in the data set in high cost areas. So in 2008, from the financial crisis, there was a bill that was passed that allowed them to raise sort of these sort of jumbo conforming loan limits to $730,000. Again, also increasing over time. So you'll see some larger loans, but just to give you context and like how much money is in the data set, this is an important definition, I think, to show. Okay, so let's jump into the notebook. So I've actually posted this to my GitHub. So if you want to download it now and follow along, you can just go to my GitHub at mcandice presentations, and it's the only thing in there. It's sort of one of my New Year's resolutions to start tracking all my presentations in GitHub. So the notebook will be there if you want to follow along. And I will jump into the notebook on one of Comet's test nodes we have, which is actually NVIDIA V100 node. So let me just close the chat here. increase probably the font size for the demo as well in the terminal. Let's see. I think I have to reset it. Okay, that's probably a little bit better. Okay, so I'm not going through the Comet queue right now, just because usually our GPU nodes are pretty busy and we didn't set up a reservation for this. And I knew we had this sort of V100 test node here that we have laying around and no one's using. So one of the things that I do in my day job is help support a lot of the Singularity containers that we support on Comet. And so I did build a new version of the Rapids container distributed by, well, sort of a custom version of the one distributed by NVIDIA. So if you haven't used a Singularity container, we won't need to talk about that. It's basically just a prepackaged mini operating system with all the software I needed to run this demo. If you are familiar with Singularity, we do keep all of our sort of supported Singularity containers in sort of these paths, so share apps, GPU Singularity. If it's a CPU only code, it'll be apps compute Singularity. So if you want to check out any of our other Singularity images, you can check them out there as well. Okay, so I'm going to start up this Singularity container with Rapids inside. So the latest version of Rapids, I think, is the 0.11.0. So like I said, it's really early on in the Rapids history. They're not at 1.0 yet. So things are changing and not everything works as you might expect. So I'm just going to start up this Jupyter notebook. Okay, close that window. Oh, I forgot. I did one mistake. I apologize. I forgot to change my working directory. So I've pre-downloaded data sets onto Comet's Scratch file system as well. So if you do have access to Comet, the data sets are available already here in this data folder. You'll see in the notebook. And the reason I had to change directories here is if you've ever worked with Jupyter notebooks, usually by default, it assumes that you can only see the directory structure under the top level directory. So since the data is here in this directory, I needed to go here. Okay. All right, so now we're in the right directory. So yeah, like I said, the data is here, single family loan forces, and I've downloaded all the different subsets. So if you do have access to Comet, you don't have to download the data yourself. You can actually point to my Scratch directory on Comet. It's publicly accessible to all the users there. But if you need to download the data set somewhere else, the code is available here in the notebook as well. So let me just close that and open this up. So a few things to note about the data sets and Rapids in general when you start working with it is, right, you do need to be mindful again of your data set size. So I sort of copied this table out of here just as a reference. So I'm going to use the largest data set that's available on the Rapids website, which is this mortgage 2000 to 2016. So the sort of 17-year version. And the data set actually consists of two subsets as we walk through the the notebook here, you'll see. So, and I'm only going to use one of them. So the one I'm going to use today for sort of a single GPU demonstration is this acquisition data set. So this acquisition data set is basically records about all of the loans that have been acquired by Fannie Mae from 2000 to 2016, or at least the conforming 30-year fixed rate mortgages that are in this data set. The other half of the data set, or I mean, not half, the vast majority of the data set in terms of size is the performance data set. And so this performance data set is basically records on all the payments on the acquired loans. Okay, so if you look at the number of loans, so essentially the acquisition data set really has records of 37 million loans, essentially, or is this 4 gigabyte number here. The performance records are on all the payments on those 37 million loans, and so that's where you add up sort of the 1.9 billion records are available in the data set. So, however, like I said, the performance data is huge if you use the full range. You could use a smaller subset to do some development work on the performance data set. I didn't really have time to do that myself, but the idea is like this data set really does force you to go to multiple GPUs at some point if you really want to analyze it all. So that's sort of it's sort of a non-trivial data set that it'll sort of really, if you need an example to use to get started with rapids and learning how to really scale something like this up, that's why I think this is a good example. Okay, so let's start walking through the notebook here. So I just start off with simple stuff. Just import the Python modules that we need. So these are sort of the first elements here are just from the standard library. The next are sort of the standard data science and machine learning modules you use on CPUs essentially. So like I said, I didn't develop a multi-GPU integration example here with Dask, but I am going to use Dask to read in the data set because it takes a long time to do it if you don't. So if you're not familiar with Dask, there's at least one example here of like how to read in the data set pretty quickly. And then again, I'm going to use Pandas only in this example. My goal was to get to scikit-learn and QML, but I didn't have quite the time to develop it. So all of the examples here really are comparing Pandas to cuDF at this point, right? And so we import the rapids modules we'll need. The next part of the notebook is just to do some setup. So I just create a section if you need to find some system environment variables. So here I'm just going to use the username as part of the configuration. And like I said, the top level directory, sort of where you want to do all the working. So essentially, wherever you started your Jupyter notebook, this is essentially where you'd want to start. Like I said, I've pre-downloaded the data to this directory already on the Scratch file system. So if you were going to use my version of the data set, on Comet, you would actually edit this and put in my username, right? Because the environment variable here is your username. So if you actually wanted to point to my version of the data set, that would be the change that you can make to the notebook. If you're following along at home on your laptop or something, don't use this data set. This is going to be the large one, so it'll take a while to download, and it'll probably be too large to get you going. If you want to follow along on, say, your laptop, if you're using it, I would use maybe just the Mortgage 2000 or 2001 version. But for the GPU example, I mean, to really show you that how much faster the GPUs can be than CPU analysis, you really do need larger data sets. So if you have really small data sets, Rapids might not be for you. You can just keep doing what you're doing with, say, Pandas, scikit-learn, and the other equivalent libraries. It's really, you're really only going to see the advantages once you go to large data sets. That's why I'm going to analyze the largest one we have right now. Sorry, Jeff, was there a question? Oh, okay. So again, just some setup to where the directory, the dataset directory is located. The next few elements there. Now this is.
There is one question.
Yes.
How large do you think is the threshold?
You know, I really wanted to do some extensive, but yeah, so the question was, how large of a data set do you really need to use to see a significant speed up? So, I mean, it's a complicated question. You'll see in the example here, there's actually, you know, some algorithms, even though they're available, or, you know, or some methods are available in cuDF that are, you know, the same ones as in Pandas. They actually run the same, just because you might not be able to do that type of transformation or task on the GPU. You actually probably, you know, there's some fundamental issues, like certain things you can't do faster on the GPU, I think is what you'll see in some later examples. So that'll be sort of be data set size independent. For the ones that do get speed up, it's really, I think you'll really have to play around with it a bit. I would say, like, you know, the data set we'll use today, we'll see, you know, speed ups of, you know, 3, 4, 5x, I think, is or even 10x, I think, in some cases. It really depends on the actual method you're calling and what the task is doing. Right, so the data set size we'll use today is around 4 gigabytes. So several gigabytes, you know, a few gigabytes is where you'll start to see significant performance increases. Right? But with the times that we'll see, you know, how much more are you waiting around? It'll still be pretty small, you know, absolute times that we'll see today. But you know, the speed up is, you can start really seeing it here at this few gigabyte level. Okay, so back to the notebook. So the next section here is just to download and extract the data set if you don't have it. So this will download and extract the data set for you, whichever one you've chosen up here. Like I said, if you're doing this on your laptop, you probably don't want to use this version. But that's the version I'm going to use today. And it'll check if it might already be available. So, all right, so since I already have it downloaded to the directories I defined above, I can see here in that directory, I have the original tarball that was downloaded and the 2 subset directories, the acquisition subset of the data and the performance subset of the data. So again, we're just going to use the acquisition data set for the examples below. So in the next section, we do some preparation just to figure out how much of the data you want to analyze. So basically, you can choose here the starting year you want to start the analysis on. So it will sort of ignore all the other files. If you say we only wanted to look from 2005 to 2016, from Q1 in 2005 to Q4 in 2016. You can change how many of the files you want to sort of import and start looking at. I'm just going to use the full data set. And so the next section just creates some lists of all the files in there between those, that time interval that we want to look at. Okay. So
question, does PDF work under Windows?
That's an interesting question. I don't know. Yeah, I would have to look that up for you. Like I said, I'm sort of new to the whole Rapids framework as well, and so I'm not sure what the Windows support is like. So it definitely works on Linux. I know that. so yeah, that's a good question. Like I said, we're going to have NVIDIA talking about this again next month as well with some other topics. So if you're really interested in sort of more underlying details and support and what's coming, they'll know a lot more about that. Okay, so we've got about 20 minutes left. So now that we're going to really start building up the acquisition data set. So we're going to basically import it. The strategy here is what I'm going to do is actually take the data set. So these are all the files that are in the 2016, or the 2000 to 2016 data set. So you see each file is by quarter. You can kind of see the sizes here. They're all, you know, between 1 and, I guess, half a gig and 2 gigs. On the NVIDIA webpage, they actually have two versions of each data set. So they break some of these data sets up into 1 GB size files. So if you look here, there's like a 2 GB version here. They would split this into two, essentially, I guess, on the GPUs. With certain methods, when importing the data, you can get faster results by having sort of more uniform, smaller file sizes. So that's just a note here. I'm not going to do that. I'm just using the regular data set files. And I'm going to import it into Pandas first, actually, and then convert it over to a cuDF data frame. So that's one way to do it, and I'll explain why I'm doing that eventually. So I guess one thing I didn't do in the slides, which I probably should have done, is talk a little bit about what's in each data set. So we're just looking at the acquisition data set. So I don't, in the next part of the Jupyter notebook here below, you'll see I'm going to define a dictionary that define all the column labels and what their data types are. So if you want to know what each column is in the data set, this is what each of those variables are and what their data type is. Okay, so if we look at the top here, the first column is a loan identifier. So it's just some ID for the loan itself. You know, who did it, the seller name, you know, so JP, so Fannie Mae bought the first loan here from JP Morgan. This 75,000 is probably the size, right? So this unpaid principal balance, so like how much does the loan should be repaid, you know, when it was made, so 1999, and so on. So there's all these other, you know, I think this code here at the end is the zip code. So, you know, how are you supposed to figure this all out? So again, like I said, if you go to the web page for the data set, there's actually some PDFs that just list and tell you what each of these definitions are and what this column is, essentially. So it's really well documented. I think if I remember, they even have like little blurbs of like what it means if one of the columns doesn't make sense. So we're not going to go into any details of a lot of the different things, but later on you'll see I'm making some calculations to answer certain questions on different columns here, essentially. And so if you need more context of the different definitions for each column, they're definitely available on the datasets website. Okay. So I'm going to define this dictionary to right, I printed out the first few lines of the data file, right? It doesn't have any column labels, right? So we're going to want to add column labels to our data frame. And I'm predefining this dictionary here really because I ran into a lot of problems with when I read in the data, certain data types aren't recognized, both by Pandas, aren't correctly recognized by Pandas from like the read CSV method. And the same is true with using cuDF, which also has a read CSV file method as well. So what I try to do is I knew what the data types are I wanted in each column, and so I'm trying to really force those data types on the read so they don't change. The two that I, probably just because of my Pandas ignorance, oh, someone drawing.
Yeah, so
yeah, is this, these two date date columns. It could be just my Pandas ignorance. I wasn't able to figure out a good way to force these two, so I'm just labeling them as objects. We're going to correct that later. Okay. So if you're not familiar with Dask, so Dask is this library that will allow you to parallelize your sort of data science workflows with Pandas and scikit-learn. And I'm learning how to use it myself. The only thing I was able to really accomplish with Dask so far, getting familiar with it, was to really speed up the read time to get the data set into a reasonable time to actually import the full data set for us to analyze here in this example. because otherwise it takes 10 minutes if you just do sort of a regular pandas read CSV. And that's basically because pandas is really using only a single thread or a single core to read in the data set. So in this example here on the this V100 test node that we have, there's actually 32 cores, and it actually has hyper-threading turned on. So that's why the setup here is 32 workers with 2 threads per core. So if you're running this on your laptop and you only have like 2 cores, you know, you should change this to 2 and maybe this down to 1. But and on Comet, right, this would be 24, and we don't have hyper-threading on, so it would be 1. So it's, you know, you got to play around with this if you're going to run this yourself. This is just what I'm going to use, and I'm going to start it up. And what you'll see here, I have top running, which will show you all the processes that start. You'll just see a bunch of Python processes start, right? So I'm using all of the cores to really read in all of these CSV files. And again, I'm using this this columns dictionary to force both the label onto the data frame and the type, okay? And this is the only thing I'm going to use Dash for today, so it'll be done in, takes about 50, 60 seconds with the full data set. So it takes 10 minutes with pandas by itself, so don't do that if you don't have to. But you can play around with it. This is something, again, you could benchmark all the methods. What I played around with a lot was pandas itself, Dask's non-distributed read CSV, the distributed read CSV, and also QDF has its own read CSV, which I said, again, I didn't use mainly because of this type enforcement that I wanted. It was much cleaner to first import it into pandas and then transfer it over to the GPU, which I'll show you.
Quick question.
Yes.
Are you reading in multiple CSVs or just one?
No, so there's multiple CSVs. So if you go back up in the notebook at the start of this acquisition data section, so here I'm literally listing all of the files that are in the data set. So there's 4 per year for 17 years. So it's reading in multiple CSVs. What's going on under the hood in all these read CSV methods, I don't know exactly. So are they chunking it in each CSV in some way, distributing it across the processes? I don't know the details, but that'd be, you know, a smart thing to do, I guess. So hopefully that answers. So I'm definitely reading in multiple CSVs, but how that's actually happening under the hood, if it's sort of breaking each CSV up into smaller chunks, I don't know. At the end of the day, I end up with a single data frame, right? So I take the Dask data frame that was imported into and just immediately dump it to pandas. I'm really only using it to read things in quickly. So I'm showing here the data types again, just to show that the types were enforced when I read in the data sets. And again, like I mentioned earlier, these dates I want to force into date time objects. So that's what we're going to do here in this next section. So again, if you haven't played around with pandas data types or not checking that your data types are correct when you read in your data, I would definitely make sure. I ran into lots of problems with when I was first started developing this. That just some of the methods aren't, you know, good at automatically recognizing certain types of data and maybe how they're formatted. So this takes a little bit of time to reformat those objects into date time objects. The reason you want to get some of the data types to be a certain type, for example, these category types. If you read these in naively, some of these category data types are actually read in usually as objects, which are sort of more open-ended. If they're actually categories, right, it limits sort of the memory footprint that needs to, you know, there's only a fixed finite number of things that object can be. So it's more efficient to have your data type set in category than say object for some of these columns of the data set. Right. And so the next section after this finishes loading or reformatting those columns, again, this could probably be quicker and done in a certain way. Maybe, you know, you can figure out how to do it on the read for me and let me know. if you're more Pandas savvy than I am. But yeah, again, this is really just to enforce that we have the correct data types once we throw it over to the GPU. Because again, I had similar problems there where even more problems there where like things were just basically thrown into as objects and not really well formatted in terms of data type. So you can see now that I've changed the dates to date time objects. Right, I'm going to start speeding up. All right, so lots of background and context, and now we're finally at our first call to cuDF, which is to basically transfer over our pandas data frame to the GPU. All right, so I'm going to show you here just on repeat. So I have my empty GPUs. Again, if you call cuDF data frame from pandas, it'll convert your pandas data frame into a cuDF data frame. So it's essentially offloading the data frame to the GPU. So we should see, there's my Python process pop up. So this is the rapids process from cuDF popping up and importing the data set. So I think it'll get to about 6 gigabytes, I think. So right, as I mentioned at the top, the raw data it's about 4 gigabytes. So there's always some overhead, right, associated with all these data structures. So you'll have to keep that in mind too. Is reading in a 4 gigabyte uncompressed data set into a different data structure. It'll create some overhead, so you won't be able to read in I think on each GPU here, it's like 32 gigabytes available per GPU. So you have to leave some overhead for the data structure as well. Okay. So again, it took about another minute to load that from CPU memory to GPU memory. But now we have both our pandas data frame and our cuDF data frame, and now we can start comparing them. And so again, I just do some type checking just to make sure everything was thrown over correctly. And now we can start using both our pandas data frames and our cuDF data frames and comparing things. So one of the methods that you might be familiar with early on when you start using pandas is just to look at, say, the top few rows of the file. cuDF has the same set. One thing that's nice is in the latest version of Rapids, you used to have to actually print each of these calls out. I guess they fixed some of the string support from cuDF since I last played around with it in the summer. But yeah, so there's different methods. You're going to see things exactly the same from pandas to cuDF. It's just going to give you the same exact results. Again, performance data, that'll be for a future version of this talk or an extended version of this talk. And let's just jump into actually exploring the data a bit in the last few minutes that we have. So one of the things you want to start doing, right, once you have your data set loaded is you want to start querying around, maybe, answering some simple questions about the data, right? So the first question here is how many loans were made for more than $400,000, right? Remember, I mentioned in the slides, right, there's this conforming loan limit, right, which was about $485,000 in 2019, right? So from 2000 to 2016, how many loans were in the data set with more than $400,000, right? So, I mean, pandas is pretty fast, right? It only took 1.3 seconds. So it's not, gonna kill your research if you wait around for a second. But if we run the same question on the cuDF data frame, it's what, 4 times faster? So if you then scale that out, and if this speed up improves even more with larger data sets, you can kind of see the advantages, right? So this is, again, a few gigabytes of data, right? So you get about a 4x speed up on this type of query, right? It's going to matter what type of query you're making. And also, right, so I go through some sort of additional sort of more complicated queries going down here. But yeah, the speed up will depend on also the method that you're calling, and sort of also on the data types of the columns that you're actually performing the queries on or the transformations on. So this, you'll see this in some of these examples. So I'll just try to run these off. They're pretty quick. So again, so you can start nesting your questions together. So how many loans were made in California for more than $400,000? So that only took about half a second. Do it with QDF. Oh, this is one of the first examples where it's like, okay, not everything is going to be exactly the same. So I ran into this the first time I did this talk back in the summer. For whatever reason, QDF doesn't quite have support for like string literals, or comparisons at least. So what you actually have to do in this case is, I go to my property state column. It's actually a category. And so you actually have to input here the integer of the category, like what's its index essentially in that column or in that category data type. So you see it starts from 0, so 0 is Arkansas, 1 is Alaska, so on. So California is number 4. So to actually perform this this query on the QDF data frame, you actually have to put in the integer, and it works fine. And again, it's faster, right? This is about a half a second. This is so it's about 2.5 times. Faster on the GPU. And you can get more and more complicated queries going. You're not going to see a whole lot of difference. Again, about twice as fast for this more complicated query. But again, you have these limitations, like your code isn't exactly the same. You have to make some modifications as well. All right. So that's like the query method, and some of the pitfalls you might run into there. The grouping data examples here are pretty interesting because you'll actually see the reason I put these the data types here is you'll see some of the variability in the speed up between doing these group by functions, depending on both the type of the data and also on the function that you're doing in the group by. So here, I'm actually just counting. I'm creating essentially a small data frame of the total loans per month, essentially, that were originated, essentially. How many loans that Fannie Mae bought were made by banks in that month, right? So this is a little bit more complicated calculation, right? It's going to take about 2.5 seconds. If you go to the QDF data frame, it's way faster, right? So it's, if there's some sort of group by function with like count, this is a significant speed up that you'll see in this example, right? And so I walk through a few more examples where you can use different functions and different data types. So I tried to label those here. So this is another example here where, again, you're going to run into problems using QDF where not everything works. So in this case, the div method here, so basically I tried to reformat the data. I wanted to calculate the sum and then just output the data in billions of dollars. Well, you can't use the div function in QDF yet. So I just had to go back and leave it all in dollars. So there's, like I said, there's going to be limitations that you're going to come across. Skip them. So you're going to run into these issues. But again, if you sort of work around some of the issues with QDF as it's still being developed, right, you're going to see significant speed ups, right? This calculating the total balance originated per month. Again, significant speed up in calculations. All right, so I'm going to just go through, and there's not a whole lot more other than just playing around with some of the other examples. So what I'm doing here in this group by section, I'm just going to sort of run these off since we're running out of time. The idea here is I'm just building up a bunch of series that I'm going to then concatenate together to maybe do some more data exploration in the next section. Okay, so again, you'll see these times vary. Right now, at the beginning, there was up to 2 seconds for the pandas calculation, or the group by method, versus down to hundreds of milliseconds. In these later ones, when I'm doing, say, a mean on a floating point number, the speed up isn't as much. So you're really going to see variability depending on what the method is you're using, what method you're calling, and some of the other subfunctions that might be there, and on what type of data types you're dealing with, right? So it'd be really nice to have some time to go through and sort of benchmark this stuff in a little bit more detail, which it's sort of set up to start doing with these examples, but I just didn't have time to sort of put that all together for you. The last section here is just the concatenation method. So again, in Pandas, what I did is with all those small summary pandas data frames, just concatenate those together into a single data frame. And again, you can do the same on cuDF. And this is one of those examples where I said, for whatever reason, cuDF does not have any advantages, say, for concatenation, right? So you see pandas is actually faster, right? So it really is the advantages you're going to see with cuDF and any of the rapids based algorithms available in the other libraries, rapids. You're really just going to have to explore whether or not it's worth your time if you rely on one type of algorithm or certain methods for your workflow, whether or not it's going to be worth it to go explore rapids, cuDF, cuML, and the other libraries. So that's sort of the summary, and hopefully sort of how far I've gotten, I guess, using rapids and pandas and things like that, and comparing the two as well. Hopefully in the next version of this talk, we'll have some sort of cuML scikit-learn comparisons, looking at sort of, my first goal is to do some cluster sort of analysis, if I can find some subset of the data here that makes sense to do that on. I just haven't figured that out yet. So hopefully you enjoyed the talk, and it gives you some context for this data set. And obviously you have a notebook here that you can start playing around with, modifying, and exploring the comparisons, at least between pandas and cuDF in the rapids framework. So with that, I will stop here. I'm going to throw the slides back on. At the end of the slides, which will eventually be posted, there are some additional links and resources and references. So again, the Rapids website's pretty nice. It has links to all these other sort of sublinks that you should go to. The Rapids blog has a lot of cool examples. So if you're curious whether or not your science or workflow might be similar to something that they've been able to do and show significant results, that's where you might want to start, just sort of summary articles on what else is available and what's possible. Again, there's some documentation on how to get started. So if my example is a little bit too complicated with this data set, if you just want to get started with just sort of the syntax and a few simple things, this part of the Rapids documentation, this start link, there's a few very simple tutorials just to familiarize yourself with the different methods that are available, say from cuDF or from pandas that are available in cuDF, and some simple Dask stuff too, allegedly. I wasn't able to get to work myself. So that's another good place to start if you want to start a little bit simpler. Then once you get a little bit more adventurous, I would definitely recommend going to the GitHub site, especially they have a bunch of their notebooks there. And the more complicated version of the notebook that I created here, where I started, was sort of a distillation of this deep learning hybrid one, where basically they use, as I mentioned, Rapids and PyTorch to analyze this data set. I don't know how well maintained this notebook is, because I saw things in there when I was looking at it again this last week that I don't think will work in Rapids anymore. So I mean, but it'll give you some additional context of things you can do with data sets and maybe how to go about it there as well. And then the last bit of documentation that's really helpful is the API documentation. So definitely use that. Oh, okay. I'll fix those links here. They're supposed to be split across 2 pages. And the last thing before if there's any last minute questions is just we have recent and upcoming Rapids training events. So Abe Stern, who's from NVIDIA, our sort of NVIDIA contact here at SDSC, he recently gave a talk to the Exceed EECS symposium, I think actually on Tuesday. So there's a link to his YouTube video already available there. I think he does cover a little bit of Rapids, but I heard it was a little bit more in depth on a different part of sort of NVIDIA's Pythonic ecosystem that they're developing. And then he'll be, I think, giving a very similar talk next month on February 20th for the Exceed webinar here. So with that, I will stop and take questions if there are any left, or if anybody's still around. I guess we still have 33 participants. Okay, great. So that's it for the talk. If you have questions, we'll stick around for, I don't know, next 5 minutes or so to see if there's anything anybody's curious about or has additional questions. You can always shoot me an email if you want. If you have problems on Comet, I would ask you to go through the Exceed ticketing system. But if you have specific things about this talk with Rapids and or the notebook, you can just email me directly. You can find my email on the SDSC directory.
One question, you just used one V100 card?
Yeah, so that's what I did here. So the notebook is set up for, where is the chat? Sorry, I'm trying to open the chat so I can see the questions. Oh, there it is. Yeah, so the notebook is set up only to do single GPU at this time. So to do the multi-GPU things with cuDF and cuML and cuGraph, you have to use sort of the Dask integration. And since I'm still new to Dask myself, I was only able to sort of use plain Dask just for to read into the Dask data frame and transfer it into a Pandas data frame, just to get the data set in quickly. To do multi-GPU, you really have to do you have to do the Dask CUDA is the module you'd load in your Python script. So there is support to do the multi-GPU, but yeah, it's not done here yet in the notebook. So one comment here as well in terms of Dask and cuDF. So in the notebook, I did go through and I read into Pandas first. And so I do want to point out again that you can read directly in from disk to the GPU through, say, cuDF and with Dask, Dask integration with cuDF as well. I just really had trouble with keeping or enforcing the data types on the different columns. So that's the main reason I did it this way, sort of preload everything into Pandas through Dask and then shove it over to the single GPU. So how would I actually do this for a multi-GPU example? I don't know yet, I guess, because I still need those data types to be properly defined once they're on GPU, and I just don't know the workflow yet of how to use Dask on the GPU to make sure it gets transferred over properly across multiple GPUs. So that's sort of like one thing on my list of things to do before I give this talk again. All right. If there's any other questions, let us know. If not, thank you.